Our project is reinforcement learning based on real-time automated valet parking. By looking at the contents, firstly, there will be an introduction of the automatic learning and also the automatic parking system and reinforcement learning will be concluded in this part, followed by the simulation framework and the reinforcement learning implementation. After that, we will present our experimental results, finally the conclusion. Let's start the introduction. First, let's focus on the problems of manual parking. One of the main problems is that the increasing sales number of cars contributes to the narrower parking space. Thus, some manual or operation error may cause damage of cars, for example, some scratches on cars. The other problem of the manual parking is that finding space to park is time-consuming in most cases and may generate additional air pollution during the searching process. Therefore, there is an urgent demand to study how to park safely and environment-friendly. Automated parking could accomplish this goal. There are some benefits of this. First, it's safe cause no scratches of car during parking in a narrow parking slot this time, and no pedestrians means no need to walk through the parking slot, and also no opportunity for theft. Second, it saves space and time by decreasing circulant space for parking and open car doors. Besides, it's environment friendly. It's reported that the parking system could reduce carbon dioxide emissions and eliminate the need for cars to drive while searching for car spaces. Thus, there is a trend for developing automated parking by automobile manufacturers. For example, an innovative automated valet parking has been developed by two companies, Meng Benz and Bosch, which is officially approved and has already been put into use. It consists of three procedures. Circumstance recognition depends on precision and the numbers of sensors. It has the function of parking slot tracking and detection. The motion planning contributes to the parking motions according to the detected circumstance through the recognition process. There are two methods. First is the indirect method, which consists of path planning and trajectory generation. The other method is direct method. The control implementation focuses on the execution of the plan motions, and for planning and control, currently most of the solutions use traditional planning methods. However, there may be some path tracking error during the process. These methods can be fragile in many cases, such as irregular parking spaces and extremely tiny spaces. Actually, reinforcement learning is a method that has the similar process of driver's practice. The agent gets the greatest reward in the process of interactive learning with the environment, thus learning the optimal mapping from environment to action. And it has three categories: value-based method, policy-based method, and actor-created method. First is the value-based method. Value function will map each state action pair to a value. However, the method performs well only in finite action conditions. Second is the policy-based method. This could directly optimize the policy-based or the sapling method and constantly calculates the gradient of the policy expectation reward about the parameters of the policy network during the training process. This method is effective in high-dimensional or continuous action spaces. However, it's easy to fall into local optimal. The actor crediting method is a hybrid method which combines the value-based and policy-based method. It adopts policy-based method to update the policy and adopts the value function and the evaluation method of the policy. So it has one actor network and one critic network. Thus, in this project, our real-time automated valet parking system is based on the actor-critic method.
Okay, let's take a look at our system framework. Our whole system is built on top of the robot operating system, namely ROS. The reason that we select ROS is basically threefold. Firstly, ROS provides flexible communication mechanism, which each module can be implemented as a node. The data can be transferred via topic, and multiple nodes can publish multiple messages onto one topic. Thus, we can easily verify the correctness of our pipeline. Secondly, we can use different programming language for different nodes, such as C++ and Python. Thirdly, ROS is designed for real-time robotics application. It is convenient to transfer the system into a real-world robot. This figure shows our whole system framework. The simulator is depicted in the red dashed block. The simulator firstly loads the simulation data, including parking map and agent information from the file system. Then, the simulator adds some random information such as randomly occupy some parking spaces and generate random goals for the agent. The whole simulation information is published to all the agent nodes. Each agent node can use the agent's current state and the arena info to generate the observation, reward, and flag of finish. Then the agent takes this information as input and generates an action as a control signal, namely the control agent K means the agent K's control signal, and publish back to the simulator. And after the synchronization, the simulator uses the control signal, push all the agent state forward according to the agent model, and finally publish the new simulation information, thereby forms the data loop. For the agent model, currently all agents are modeled using the kinematic basic model. Since the velocity of vehicles is low during the parking maneuver, so the kinematic basic model is accurate enough in this situation. Kinematic basic model simplifies the vehicle into a two-wheel model. The differential equation is shown here. Notice that the control input of the model is the steering rate and the longitudinal acceleration. The model takes control signal as the input and then pushes the agent state one step forward. For the parking environment, we add up multiple elements here. Firstly is the ego vehicle, shown in gray. And the static obstacles includes the gray cylinders and boundaries. The parking spaces is shown in red polygons, and the obstacle vehicles are those pink boxes. Finally, the target parking space is the sign rectangle. Then we move to the RL implementations. The task of the project is a navigation task. We are trying to find an optimal policy that drives the agent towards the target state. The state variables is a tuple of vehicle states. Notice that the delta F is a steering angle bounded by the maximum steering. G is a gear status for backward and forward moving. The action space includes 4 elements: the steering ratio, the brake and throttle ratio, and the gear changing signal. For the observation, we do not inject noises into the state variables, which means that we have a perfect observation on equal states. For the environment information, we generate an obstacle map, and for the target parking space, we also generate a cost map. These two maps are both rasterized maps that encode the spatial information. We also add a virtual range sensor to mimic the ultrasonic sensors or the LiDAR system of the automated vehicle. The range sensor returns the distance between the vehicle and the surrounding obstacles. For the reward function, here we design 4 kinds of reward. The first one is the step rewards. For each simulation step, we add a small penalty to the agent to encourage it taking maneuvers rather than stay. The second one is the success reward. If the ego agent successfully moves into the target parking space, we give the agent a large positive reward. Thirdly is the collision reward. If the agent collides with the surrounding obstacles, we give the agent a large negative reward. And finally is the improvement reward. Since the vehicle is under the follows the non-holonomic constraints, here we use the red S-shaped path to describe the distance between the ego agent and the target parking space. Every simulation step we calculate the difference of distance with the last time step so as to get the so-called improvement of the agent during the current time step.
The algorithm we use is the actor-critics method, which is the combination of policy-based algorithm and the value-based algorithm. As shown in this picture, there are 2 parts of the algorithm, the actor and the critic. The actor takes the states and outputs the so far best actions. It controls how the agent behaves and interacts with the environment by learning the optimal policy. The critics, on the other hand, evaluates the action generated by the actor by computing the value function. The goal of this algorithm is to make both of the 2 parts work together and do their best job. In the training phase, the actor is optimized by maximize the value predicted by the critic. One major advantage of this algorithm is that the critic can propagate the gradient to the actor continuously. This is crucial for most of the reinforcement learning algorithm. In our auto parking task, the reward from the environment is sparse and delayed. Only if the car is parked to the parking area or collided with the obstacles or other cars, there will be a reward from the environment. So with the critics, the actor can get gradients continuously. Considering this factor, we applied this algorithm to our auto parking task. The observation we use is introduced by my teammate Zhang previously, and here the introduce we use has 2 parts. The first part is the 1D part, and the second part is the 2D part. The 1D part contains the virtual rangefinder data and the ego state of the car itself. And for the 2D part, the target map and the obstacle map forms the 2D input for the convolutional neural network. The structure of the network is shown in this picture, and the 1D inputs are processed by a series of fully connected layers to generate a feature vector to represent the information in the 1D features. Meanwhile, the 2D inputs are processed by a series of convolutional layers and pooling layers to get the representation of the obstacle map and the target map. And then the feature from the convolutional layers are applied several fully connected layers to get a 1D feature, just like the 1D part do. And then the feature from the 1D input and the 2D input are concatenated together for the actor and the critics. The actor and the critics are formed with fully connected layers, and the actor predicts the action, and the critic predicts the Q value. And then I will introduce our experimental results. In this video, we show several steps of the training procedure. As the training procedure takes a very long time and the network is still training at this time, so far the agent has the ability to avoid some obstacles, but is still struggling to park the car into the parking area accurately. And besides, based on our observation, the performance of the agent is heavily related to the hyperparameters. The hyperparameters of the training should be fine-tuned carefully, and we will update our training result on our GitHub repo.
The last part is our conclusion. First, we implement a real-time simulation framework for automatic parking. Second, we design a deep reinforcement learning-based agent that can automatically explore the environment, interact with the environment, gather reward from the environment, and improve the internal policy of the agent. Last, we noticed that currently the training of the proposed actor-critic agent is not stable. We think the problems are basically threefold. The first is the reward function need to be carefully tuned. Second is that the hyperparameter really matters. So the hyperparameters of the network and the optimizer is also very important. Last, the agent maybe cannot learn such a complicated task. Curriculum learning can be involved in the future. That's all for our project. Thank you for watching.